All right. So 7.3 is a continuation of 7.1 and 7.2, as you've noticed through all the chapters. And 7.3 is when we really get into what we did in the previous chapter in 6.3. If you remember 6.3, it was the conservation of mechanical energy. That was the whole topic. MEI equals MEF. That was whenever an object, a single object, is moving, its energy is constant. Its energy might be kinetic right now, and then it turns into thermal energy in the form of friction. It might be potential right now, and it falls and it turns into kinetic in the form of velocity. So we saw in the last chapter how conservation of energy gave us a balance. Here we're going to look at conservation of momentum. Very similar. But this involves a multiple body system. So not one object, but at least two. Yeah? At least two. So that's what we're going to be looking at here. Very different there. But the conservation aspect is the same as last chapter. But we are looking at multiple objects interacting now. These two objects, you know what they can do? They can come together like this. Take a look at the erasers. They can come together and hit, and cause the other one to move. They could start together and explode. They could both be moving and come together and hit. So there are many options to this. They could actually, this is the craziest one, they could come together and stick together and move. Okay, so we'll continue with this tomorrow. I forgot it was a D there. I'm thinking it's 2:30. If you need anything, I'm going to start. So last class we quickly talked for about a minute and a half or so about the idea of conservation and how this involves a two-body system. Okay, so remember the idea was a two-body system. Whereas with energy, we looked at the energy of a single object as that object moves. That was the only thing we cared about. But with a two-body system, we need to recognize that upon these collisions, we have multiple velocities. So that's where this is going to come into play. Let's jump right into the first slide here. Now this first slide is literally the same thing as conservation of energy, except instead of potential and kinetic energy here, I have this big symbol, which again, what does that symbol mean? The sum of. So the sum of all of the momenta, plural momenta before any interaction equals the sum of the momenta after the interaction. It's physically what's happening here. So if we think about two objects colliding or pushing apart, let's assume they both have velocities to start. So let's take these erasers, ready? We're going to slide them together, and then they hit, and they kind of rebound a little bit. So initially, this one had negative momentum. This one had positive momentum. That goes in here and here. For object 1 and object 2, before, equal sign represents like before the interaction. After the interaction, we have these parts. And after the interaction, again, I'll toss one faster than the other. So after the interaction, we saw that because this one was much faster, this one got kicked off a little bit. So the first object, which had a positive velocity to start, rebounds with a negative velocity. The second object, which had a negative velocity to start, hits and rebounds with a positive velocity. So the concept here of conservation makes sense because you're looking at, again, like a balance. We're looking at a balance. Now, what if this object isn't moving to start, and only the first object is moving? What does that equation simplify to? Or what can I drop off? Stationary. Okay, stationary. This one is moving. What can I drop off automatically before the collision? Look at the equation. Not mass. I like the idea because mass dropped off a lot, but not mass. If the masses are all the same, you can drop off mass. We'll get to see that soon. Not mass right now. Again, the second object is stationary. Stationary. Yeah, the whole term, because velocity is 0, but if this is 0, it's 0 times mass, which is 0. So if only one object is moving before the collision, like this right now, I'm only having m1v1i. This is not existent, because the second object has no velocity. Yes? Then they collide, and it kicks that object off, and maybe this one rebounds a little bit. So after the collision, they both move. So they both have velocities after the collision. What if, hypothetically, let's see if this will work, I don't know if it does. What if all of the velocity from this eraser goes into that eraser? So watch this example. Let's see how well it works. So this one has velocity. And let's assume that as soon as it collided, it stopped. It was close to it. It didn't actually stop. If the first object stops after the collision, and the second object wasn't moving before the collision, how does it reduce in that case? What happens to the equation then? Because this is a general equation, assuming that there's two objects moving before the interaction, two objects moving after the interaction. But I'm telling you, only this one's moving before, and only that one moved after. What can I do with the equation? How can I make it a little more simplified? What do you think?
M1v1i equals M2v2f.
Well done. Well done. And that's the concept again, that the first object was moving to start, the second one wasn't, so this would go to 0. And then after the collision, all that momentum from the first cart transferred into the second object, and the first object stopped after the collision, so that would also go away. So this one wasn't moving to start, this one was, but then this one stopped, and this one started moving. So this equation is a generic equation. What if I have, and we're not going to have it in this class, but hypothetically, what if you have 3 objects? What happens? You don't have to give me the whole equation, just tell me, how would this alter if I had 3 objects?
You just add another equal sign and have the same formula.
Careful, not another equal sign, because it's still 3 objects colliding all together. Still one collision only one major collision. You'd have an M3V3I here and an M3V3F here. Okay, so not another equation itself, it's still one equation. So the example that's really the easiest thing to think about for conservation of momentum is billiards. If you've played pool before, pool is a perfect example of perfect transfers of momentum. We're going to talk in section 7.4 about the types of collisions that can occur, where the objects can maybe like deform a little bit, or they could technically stick together. A simple or a good example of the sticking together, if you've ever seen at like you haven't seen this, but at a train yard, the way trains actually come together, there's a little locking mechanism that engages between the trains. So this train is coming in, it's coming in real slow, this one's stationary, it clicks into place and the lock engages. The lock engaging them allows them to move together afterwards. The caboose, right? The caboose of the engine that pushes it along. So they move together afterward. So that's a whole other kind of example we're going to see where they stick together after. Another good example, if you've ever, again, not you, but if you've ever seen a car accident, sometimes the cars will actually fuse together. So if you get, specifically when you have rear-ending situations. So on the highway, if one car rear ends the other, sometimes the front end of one car will either like literally jam itself into the back of the other car where they actually stick together. Sometimes they could actually melt together if there's enough friction there involved, if it's going at a high enough velocity. And that's fusion. We'll talk about what happens to that, but that's the same concept as the trains locking together. Now, the other part of that, instead of 2 things moving separately coming together, if they start together and then move separately. In that example, the easiest way to think about it is like any sort of explosive. The easiest example, and it's not something maybe you want to even think about, but grenades. Grenades, when shrapnel is sent off in every direction, the piece of shrapnel being sent that way is easily balanced by a piece that way. A piece that's moving this way gets balanced by the momentum this way. So a piece of shrapnel or a grenade splits into like thousands of pieces of shrapnel. The overall momentum of the system, though, if the grenade is sitting still, the momentum right now is 0. When it explodes, every piece of shrapnel will be balanced out by another piece of shrapnel, yielding still an overall of 0 momentum. So if this one has positive momentum, this one will have negative. And if you sum those values together, you get back to 0. Because right now, if I literally look at this as a grenade, it's got no momentum. So that means that this must be 0 on the left-hand side, the whole thing. Another example, I'm just trying to give you guys examples so when you see in your book you'll be familiar, is the one we're going to do in class actually too. 2 ice skaters standing together, and imagine they just push off of each other. And the reason it's ice skaters is because ice is very low friction, so we don't have to worry about energy loss. So if 2 objects are together and they push off each other, it's the same thing as a grenade. It's literally the same model, except with a grenade you have millions or thousands of pieces of little mass, right? The skaters are like 2 pieces of shrapnel. If this skater is really big, and this is a really small, so this is a dad and then the child, right? and the kid decides to try to be funny and push his dad down. The kid will try to push the dad who's here. The dad might move like this. The kid's probably going to move like that. Much lower mass, much higher velocity. Much higher mass, much lower velocity. But still having a balance. This would still be 0 in that situation, because to start the problem, they're both standing at rest. And then they push off. That means that this will be a positive and this will be a negative, or vice versa. Okay, that's my hand. Pop up for a second. Yeah. Anytime the system as a whole is at rest to start, you start with a 0 initial momentum. So this whole side of the equation becomes 0 in that case, if they're starting from rest. Okay, so I gave you some. What I want to do is look at some of these and be able to come up with the actual equation. So first we've got a hockey player, swings a stick. The mass of the stick is about 1 kilogram. I don't know if that's reasonable. Any hockey players? Anybody play? Is 2 pounds about a reasonable amount for a stick? I kind of just pick. I know James does. I do know that. I'd say 2 pounds is probably reasonable. At a hockey puck, that I did look up. The mass of a hockey puck is 125 grams. He swings the stick with a velocity of 40 meters per second, like a slap shot, as fast as he can swing. Maybe too fast. And after that, after the collision, the stick speed is now 30 meters per second. So if you want to think about baseball, or if you play softball, think about softball or baseball. When you swing a bat, you hit the ball. What does the ball do? The ball slows down your bat. It's like an opposing force. So when you hit the actual ball, you might have a velocity of, and this is true numbers, guys like Ken Griffey or Barry Bonds, some of these really good hitters back in the day, even now, would swing with velocities, absurd velocities in the batswing, like 120 miles an hour batswing. And they would contact the ball, and it would reduce significantly, maybe to like 110. Where is the energy going? Where is the momentum in the bat going? Into the ball. The ball is taking on that momentum now. And that's the concept of conservation we're looking at here. The speed of the stick has to go down, because the momentum that the stick loses goes into the hockey puck. The momentum that the bat loses goes into the baseball or softball. And the idea of balance of momentum shows us that if we lose somewhere, it's got to be gained somewhere. Just like energy. That's why I keep saying it's very much like energy. When we lost potential and it fell to the ground, we gained kinetic. When we throw an object up and it lost kinetic, it gained potential. There was a little bit of a balance there. So the momentum has to be balanced here as well. So I start by recognizing that the stick is moving first. It's the same thing about the puck moving first. Is the puck moving? Doesn't say it, right? It doesn't say this. Who knows what a one-timer is in hockey? If you say a one-timer. It's like in soccer when the ball is passed to you and you shoot it right off the pass. You don't actually stop, settle the ball, and then shoot it. The ball is coming towards you and you take a shot right off the motion. So it's like a ricochet or a rebound. In hockey, sometimes the puck is passed, and as it's coming to the player, he or she, or in this case mainly he in the NHL, will slap shot or wrist shot. If they control it, they might stop it first and then take a shot. So we're assuming here that the puck is stationary simply because it doesn't say that it's moving. Okay, it doesn't say, oh, I'm sorry, here we go. Initially at rest. So we can use that to help us. So the first object, which is the actual stick, has a velocity initially of 40 meters per second. And then afterward, the stick velocity is 30 meters per second. Okay, that's the stick only. Subscripts are going to get a little bit messy here. They're going to get a little bit messy. You have 2 objects and you have 2 times. It's object 1 and 2 or object A and B. Whatever you want to call it. If you like A and B better, last year students liked A and B because the 1 looks like an I. So they got confused with that. Okay, but this is the number 1 here, and that's the letter I and the letter F. For before the collision and after the collision. Or interaction, we should say, not just collision. The hockey puck is not moving at first. And the question says, if the puck is at rest, what is its velocity after the collision? So that's what we're trying to solve for, V2F. And then finally, we also know the masses of each. The hockey stick has a larger mass than the puck. Proportionally, how different are they? How many times larger is the stick than the puck? Anybody know their math and their decimals well enough? What's 0.125 as a fraction? Anybody know that one? 1/8. Very good. So the stick is 8 times more massive than the puck. Let's keep that in the back of our mind. Let's keep that somewhere in the back of our mind. The stick is 8 times as massive as the puck is in this problem. It'll play a role. So we've got the scenario, and for all of these problems, we're going to start with the same governing equation. P before equals P after. Okay, momentum initially equals momentum afterward. So I could say I've got two objects before and two objects after. The puck is not moving to start, so I can go ahead and put a 0 here. I'm calling the puck object 2, so I can drop that off to start. It's not moving. The stick is moving. Even after the stick hits the puck, it's called follow through, right? You follow through your shot, the stick is still moving. So there is velocity here for the stick, and there is velocity here for the stick, and those are the numbers right there. The mass of the stick goes here and here. The mass of the puck goes right here, and we can solve for the velocity of the puck. So if you want to, this is one of the times throughout the year that I actually have encouraged students at times, if you want to plug in numbers, plug in numbers. Okay, because there's a lot of stuff with variables, and it gets really messy. So coming up with a generic solution can sometimes be a little bit tricky. Not just tricky, just has room for error. So if you want to plug in numbers earlier, that's not a bad idea in this kind of a problem. I'm going to still move things variably. Okay, I'm going to move things over. Okay, I'm just rewriting it so that it's clear what I'm doing. Then I'm going to take the M1 V1F and move it over to that side of the equation. And then finally, I want to find the velocity of the puck after the collision, so I should divide by M2. Okay, so if I'm doing this with algebra, a little bit of math, or a little bit of substitution here, I would substitute at this line at the very end. But again, it's the same thing as plugging in up here and solving for V2. Doesn't matter which way you approach the problem. Before you give me an answer, the stick itself had a velocity of 40, hit the puck, and went down to 30. So how much velocity? 10 meters per second loss, right, in the stick. 10 meter per second loss in the stick. Don't give me an answer, give me an idea. I don't want a number. Will the puck gain 10 meters per second exactly, what the stick lost, less than 10 meters per second, or will it gain more than 10 meters per second? Which one will the puck gain? The same amount of velocity the stick lost, less or more? What do you think? Sarah?
More because the mass is less.
There it is. That's the exact right answer with the right reason. The mass of the puck is much less. So although the stick lost only 10 meters per second of velocity, the puck is going to gain more than 10. What does the answer turn out to be, actually? How much does the puck gain in velocity? What do you get? 80. Now make sense of it, please. Somebody else? Sarah got the first part of this. Why does 80 make 100% sense? It really does. How come a final answer of 80 meters per second makes sense?
Since the stick is 8 times heavier than the puck.
Yes, that's it. We said earlier, I asked that number 8, right? The stick's mass is 8 times more than the puck. Yes? So if the stick loses 10 meters per second, it's losing 10 meters per second kind of times 8, because it's 8 times more massive than the object it's giving its energy, or momentum in this case, to. So we think about the change in velocity as 10, and 10 times 8, 8 being the factor of increase in their masses, gives you the 80 that the answer is. Okay, so there's a reason behind the number you get as an answer. So let's jot that down, right? Let's jot that down. If we have a more massive object attacking a less massive object, which is what this is, more massive being the stick, less massive being the puck. If there's more massive attacking less massive, it means that that little object is going to gain more velocity than the big object lost. The smaller object, or the less massive object, will gain more velocity than the more massive object, or the bigger object, had lost. In this case, it's 80, because it's 8 times more massive. 8 times more massive. Let's look at a second problem to make a little more sense. Okay, we're going to change it up a tiny bit. Here we've got a sample example where the objects are the same. The objects are the same. Alex, what did you tell us earlier? If the objects are the same, what do you think we can do with this equation that we've had? Yeah. So with this problem, we're going to take a look. We're going to see a soccer ball is kicked down the field. It collides with another ball that's at rest. So here's the first one. And look what I'm going to put right away. I'm not even going to write the actual part of the equation because the second soccer ball is at rest. So I'm just going to put a 0 or just not even write it. The first time through, I wrote it. And then we crossed it off because that general equation has 4 parts, right? So I wrote it to just appease you for a minute. But at this point, we've done one problem. Let's look at the second and say, it doesn't make sense to even write anything because the second object isn't moving to start. It says, assume the soccer balls are identical. So on the top right, let's write, okay, M1 equals M2. M1 equals M2. If the ball that's moving before the collision has a velocity of 12 meters per second east before it hits the other ball, so the one that's moving before the collision, that's this right here, 12 meters per second east. East is positive or negative? East, positive or negative? Positive. West is negative. And it doesn't actually matter as long as you're consistent. If it's moving with that velocity before the collision and a velocity of 4 meters per second east after the collision, so the same object after the collision, then what's the velocity of the other ball that was initially at rest, right? The second object that was initially at rest, what's its velocity after the collision? What is V2F? And we have, again, M1 V1F plus M2 V2F. So that's my overall equation again. It's the same equation. I have initial and final velocity for one object. One of them is at rest, and then it moves. Since it's at rest, we ignore this part. Come on.
Oh, no, that's my question.
Because it's at rest to start, its velocity is 0. This is going to be M2 times 0, which is just 0. If this had said it came to rest afterward, then this would have dropped off also. If the first object after the collision had stopped and transferred its momentum, and it just stopped, we would have said that equal to 0. But it didn't. It's still moving. So here's your scenario. Ready? Soccer ball number 1 right here. Moving with a high velocity of 12 meters per second. Hits the other one, and the other one gets off, but this one slows down. This gets launched off somewhere, but this one still moves with a velocity of 4. So it was moving really fast. It collided, launched that guy, and then slowed down. It didn't actually stop, and it didn't get rebounded. Okay, it says again that it's still moving 4 meters per second east. The other one was 12 meters per second east. If it got rebounded, what would it have said? If it was moving this way after the collision, what would it have said? It would have said west. It would have said west right here. Okay, if it were rebounded. It's not rebounded, it's trailing. It's trailing the other object. So I asked about pool. How many of you actually played pool before at some point in your life? How many of you played pool where they actually know what they're doing when playing pool? Be honest. Okay, awesome. So, do you know that if you hit the pool cue ball at different locations, it puts spin on the ball differently? So if you need to put backspin on the ball, you hit the bottom of the ball. We call that English in pool. The concept there is that you're creating something where it's spinning as it's actually, so it's moving forward, but it creates a little backspin where it hits, it wants to come back off of the ball. Or you could have ones that follow your shot as like a trailer, and that's what we're looking at here. The soccer ball that does this. And it still trails the other one, but the other one moves faster. Anybody have any idea what they think the answer will be without even doing any math? Think about the last example where one mass was 8 times more than the other, which affected our answer. But here, they're the same objects. It's literally the exact same object. Peter, what do you think?
Final is going to be like 3 times less.
Why?
Because it's 12 to 4 ratio.
So Peter's looking at the velocities, and he's looking at the ratio, which normally I'd say that works, because we look at ratios, right, for factor of increase. It's not a ratio this time, but I like the way you were thinking about it. It's not a ratio this time. Momentum lost by one object must be the same or gained by the other. So what's the number going to be here for V2F? 8. And where are you getting 8?
Equal, so the mass drops
So you did the math real quick.
Yeah.
You could also just look here, right? See? This object lost 8 meters per second of velocity. Where's it going? Into the other one. It's all going in there because they're identical objects. There's no proportion this time. And to prove that mathematically, we can write this equation without any mass. Because all the masses are the same in this problem, they all drop off. Only because of this statement right here. Whenever the masses are the same, it's like having the same number multiplying every part of the equation. We could just get rid of that number. Call mass 1 and mass 2, just call them all m. And then you would have m here, which doesn't matter, m, and the m would just drop off. So whenever they're the same, you can just call them m if you want to make it easier. So yeah, this equation becomes this. And this was 12, and this was 4. So what must the other object be? It must gain 8. Okay, it started with 12, the first object. It collided, reduced to 4. Where'd the 8 meters per second go? Into the second soccer ball. So the second soccer ball absorbed all of the momentum from the first one that it lost. This one lost a certain amount of, I don't know how much momentum it lost. Momentum, remember, is mass times velocity. Since we dropped mass, this is not telling me how much momentum was gained. This is telling me how much velocity was gained. 8 meters per second of velocity was gained in this scenario. I want you to see that the equation didn't change. That's the key to write down. The starting equation was the same. All we did was drop off one of the variables because it was not moving. I want to start the next one, which is fine, but I want to at least get an idea and look at it. A person has a certain mass. They jump off of a platform, so imagine you jump off the desk and land, with a velocity of 5 meters per second west. If he or she lands on a cart, don't try this at home, but this is like, have you ever jumped into a shopping cart before and just rode it down a hill?
Yeah.
When we were kids, that was like a thing to do. I don't know if you guys do that anymore. We would like steal shopping carts and ride them downhill. Very, very unsafe. Do not do this at home. I didn't tell you to do this. But this is pretty much it. It's like if you just like kind of dropped your brother into a shopping cart with a little bit of a push at the same time, he'd start rolling away. That's what's happening here. A good example, how many of you like to go sailing? Sailing? Okay. So when you step off the dock onto a boat, technically speaking, you're adding your mass to it, right? So if you had like a rowboat, like a little tiny rowboat, like in Central Park, not a real boat, a big ship or something, and the rowboat was untied from the dock, and you just jumped off the dock and landed on the rowboat, what would happen? Yeah, you would sail away, or you would start to move away with the boat, right? Hopefully have oars. But this is that exact example right here. Okay, it's a person jumping, landing in a cart that has wheels on it, and they have a combined velocity afterward. Why is it combined? Because the person lands in the cart itself. So when we're visualizing this, here's mass 1, here's mass 2, and then that's the before, and then afterward, they're literally mass 1 plus mass 2 stacked together. And it's moving. So this one was moving initially, and now the together part, they're going to be moving. The cart was not moving initially. It was initially at rest. So this is you jumping into the cart. This is you sitting on top of the cart. So the overall mass is one object now, and the mass is, we call this lumped. It's a lumped mass. Lumped mass. That's the key word there. Okay, when two objects combine. Try to finish this yourself if you'd like to. You can look at the video over the weekend. We're going to finish up 7.3 for sure next week. Interaction now. We've got M1 V1I plus, and then that's a 0. Because the second mass is not moving. This guy is stationary. He's not moving at all. But the first one is. So there is momentum for the first mass. Then after they interact, the first mass lands on top of the second mass, and they move together. If they move together, what can I say? If they move together, what can I say? What do you think is the conclusion there and make it easier on you? What would I write the right-hand side? Read it. M1 plus M2. Okay, because their masses are physically one mass now. And there's one velocity that we have to worry about. There's no need for V2F or V1F because both objects are moving with the same velocity after the interaction occurs. So this velocity does not need a specification. You don't need a 2 or a 1 here at all, and you don't have to worry about distributing it. This is one mass after the problem, after the interaction. What is it, 70? Yeah. You're 50, the card is 20, so this total mass is just going to be 70. So whenever write yourself a note, whenever two objects stick together or fuse together, I think that was the word I used, whenever they fuse together, the after is going to have a lumped mass. This is before, and this is after. The after part will have a lumped mass, lumped sum mass. And if you lump things together, it means to categorize them together. So we're lumping these masses together into one overall mass. So it's a sum on the right-hand side. It's possible to have it the other way around, where two objects are moving together at first, and then one object is launched from the other object. You'd have a lumped mass over here in that case, and then since it launches the second object, they'd separate over here, so you'd have two parts of the equation over here like we had last class. But again, because they're stuck together, there's only one object in the after part. Yeah?
Aren't those two sides the same thing?
Are they the same thing? What do you mean?
Like if they're both, but are those?
Well, this is M1, which is only 50.
Yeah.
And this is M1 and M2, that's 70, so they're not the same. Those are different numbers. This is the velocity we're looking for. This was the velocity that we started with. So what do you mean by they're the same? What do you say?
I just feel like it's like the same numbers on both sides.
Well, let's figure it out. I mean, the theory of conservation of momentum tells us that the same number should be on both sides in the end.
Yeah.
But these individual numbers are going to be different. But if this whole answer on this side turns out to be, I don't know, we don't have that number. Say this turns out to be whatever the product is, 5 times 50, negative 250, or 250 in this case. Well, this side has to be 250. That's the idea of conservation. But we don't know. We have to see what they come out to be. So the first person's mass is 50. Let's jot that down in the equation. The velocity. What do I write? I drew this diagram kind of backwards, to be honest. I just drew it last class, I think, right? And I drew this diagram as if the object were jumping east, but what does it say in the directions? It says they jump west. So what do I have to do? What do I have to do?
Make velocity negative.
Yeah, the velocity with which this person jumps is actually negative. So if I'm drawing this diagram, you need to take this and just mirror image it, please. It's actually like this, really, this problem. Okay, where the mass gets launched and lands on the other mass here, and then later on, they're just moving together after they land on top of one another. That's actually what's happening in red. Okay, I drew it all to the right, ignored the last time we had done this. I think we kind of rushed right at the end of class last time to go through this, so it started. So this is really what's happening when you think about west. So this velocity is negative. That's why this is negative 5 or west. So this is negative 250. That's kind of what I was getting at here on this part. Now this mass is 50 and this is 20. I can add those together. I get 70. And then I solve for VF. That's my goal, to figure out the velocity of a two-part system after the interaction. Okay, so first object lands on top, and then, well, in this way, lands on top, and then they start moving together afterward. That's what we have to visualize here. What kind of an answer am I going to get? What kind of an answer right away? What kind of an answer? Not what the number is. What kind?
Negative.
Negative. Definitely. Make sense of it, please. This object jumps with negative velocity, lands on the cart. They're not going to start moving backwards out of nowhere, right? It's going to move with the same motion. So it's going to move to the left or west, which is going to be negative. So VF should be negative. What else about the value of VF should I know, even before I do the computation? Before I do the calculator work and all that stuff, right? What else about VF should I kind of know for this problem? And use logic here, really. How about something about its relative answer?
Should it be smaller?
Then?
Than before because the diagonal was before.
Very good, Alex. Well done. So let's go over that. This object has a mass of, what was it, 50, right? 50 kilograms. It is launched or jumps from this surface with 5 meters per second. Suddenly, it attaches to a cart. And now the mass is 70. It's not going to speed up. It's not logical to speed up. It would be like saying, you know, as snow accumulates on the roof of your car, it's going to make the car go faster. It wouldn't be logical, right? If you suddenly are carrying more weight, can you go faster? If anything, you go slower. So the answer that you get here should be less than -5 for VF. It should be something smaller in value, in magnitude, than the -5. Okay, Steve, what do you get?
Oh.
Or what do you have a question? Go ahead.
Well, yeah.
Go for it.
Well, it's -3.57. 3.57.
Okay, and your question, go.
When I'm just thinking of it, when a person jumps into a car, that initial
Boost.
I mean, and it says, will the combined velocity be immediately after landing? I would just expect it to be higher because.
Well, if the cart were moving, then sure. The cart's not moving here. Think about it. The cart's at rest. You're right. You landing in the cart gives it that jolt, right? Which is like giving it momentum. And that is the idea. But you have a lot of momentum and some mass. Now you have more mass. So the momentum that you're giving up goes into the overall system. But if the cart were moving initially and then you jumped on, then it would be a greater number than the 5. Because you and the cart would have momentum, right? Whereas right now, only you have momentum, and you're giving some of that to the cart. So what has to happen to your velocity? To give up some, you have to go a little bit slower, because you're kind of giving that velocity to the cart. Okay, that's the rationale behind it. But yeah, if they were both moving, then you would be helping the cart, and therefore be moving a little bit quicker. It's a good question. Other questions on this? I'm trying to get into more of the understanding of the answer with this topic, because a lot of this topic, like energy methods, was very conceptual, or is very conceptual here. So I'm trying to ask you guys questions like, why does it make sense? Or why is it still negative? As Steve just pointed out, like, why is the number suddenly a little lower than -5? Okay, because suddenly you have more mass that you're having to move along. The math itself is not very difficult in this section, you're noticing. I mean, we did momentum impulse with 7172, and now it's just going to be this formula over and over again. Depending on the scenario, things change. Maybe we'll have this in the next problem and not have this. Maybe they won't end up together in the next problem. Figure it out. But every problem is pretty similar to the previous problem. It's really just our conclusions that we draw that may be different. All right, let's go to example 4. 2 ice skaters are standing together at rest in the center of the rink. Okay, in the center of the ice rink. They push off each other to move in opposite directions. The mass of one person is 60 kilograms, the other is 40. The velocity of the person with 40 kilograms after pushing is 7 meters per second. What's the velocity of the other person after pushing? So let's take a look at the erasers here. So here's 2 people standing together at the ice rink. And suddenly, they push each other. They're going to naturally separate. One will go further than the other. One will go faster than the other based on their relative what? Mass. If you're bigger, you're not going to go as fast. So if you try this and you're 2 people ice skating and one is like a small child and one is an adult, someone your size or bigger, and you push off with the small child will go off real fast and you will go off very slow. Okay? It's very similar, and I don't think I've even showed this video. I'm going to show it one of these days, maybe when we review. There's a video of the blob, I think I mentioned it at some point, which is conservation of energy, really, not momentum. But the concept is similar. You put like a really, really, really lightweight kid on the end of like a blow-up bounce castle, and you take somebody that's heavier and jump down and land on the bounce castle, what's going to happen to the kid that's sitting here? He's going to get launched off the end of it. And in the example, it's like, I forget what movie it's from. I think it's called like Camp Nowhere or something. But the idea is that it's a big bounce castle floaty device that's in the water. So the one guy jumps off of a platform at the top, lands on this float device. The kid who's on it gets launched like 50 feet in the air. And even though the one guy jumps from a certain height, the kid ends up going far higher than he jumped from because his mass was so low that even though this guy had a velocity of some amount, almost all of that transferred in, and this kid came off with a higher velocity, so he got launched off instead. Try it sometime. It's fun. If you can get that set up, though, you'd have to go to like a summer camp or somehow have that. But that's physically what's happening. Similarly here, with 2 different masses, they'll move at different rates. So I've got object A and B. I'm going to call them A and B because it says it in the problem, but I can call them 1 and 2 also. Oops, not 70-40. We're told that the velocity of the second person after pushing off, take a look at what I'm writing, that's VBF, is 7 meters per second. Again, the velocity of the second person after the interaction means F. That's what we have. Before the interaction, what is the momentum of each object equal to? Before the interaction in this problem, what is the momentum of each object equal to? 0. Because they are not, keep going here, because they are not good, moving. The velocities are nothing, they're 0. So the overall momentum of the system before anything happens, before the interaction, or just simply before the equal sign, think about, right? Before the equal sign, the overall momentum is going to be 0. That's for sure. Because they're not moving. I could write VAI is 0. VBI is 0. Okay, because they're both not moving. But in some of these problems, it might even just be quicker to not even list them in those parts and just drop them off out of the equation. VI comes here, or VAI is here, and VBI is here. They're both zeros, so 0 plus 0 is 0. And our goal is to find out the velocity of this person after the separation. So we're trying to find out what VAF is equal to. How fast will the heavier person move? Don't come up with an answer, please, yet. Don't come up with an answer. Think to yourself and use logic. This is where I guarantee you a multiple choice question comes into play. 100%. Okay, I ask multiple choice about this stuff every single year. If I were to look at the setup, what can I conclude without calculations? What can I automatically conclude? Give me some stuff. Give me some stuff. Alex, start us off.
The velocity will be much smaller.
Okay, so he sees that this is a small person with a large velocity. So a large person, to balance that, will have a small velocity. Agreed. So the number itself over here will end up having an absolute value or magnitude less than 7, for sure. Good point. Chris?
It would have to be negative because he's going the opposite way.
It has to be negative. Those two things are what we conclude. It's got to be negative, and it's got to be a velocity smaller than this one, because a small mass means high velocity. High mass is going to mean a lower velocity. If there's an exact balance, which there is here. It's two objects just moving apart. So to see that mathematically, we can write it out. That's what our equation looks like. I can plug in at this point to make it easy. I know a lot of you have been doing this more and more lately. That's fine. With these equations, it might be nice to plug in earlier. There are certain times you're not going to be able to plug in, and I'll get to when those are. Or we will get to when those are together. So that's what I've got. Okay, mass is the bigger object, smaller object. Here's the velocity. So this has to be a negative number for negative and a positive to come out to 0. So Chris is right, it's definitely negative. And Alex is right by seeing that this comes out to 280. This means this has to be a negative 280 in order for that to add up to 0. So the only way for this to be negative 280 is for this VAF to be smaller than 7. Okay, what do we get for VAF when we solve? The velocity of the larger person. What do we get for VAF? Any numbers here? Couple keystrokes, right? That's all it takes. Thank you. Negative 4.6. Repeating, right? Okay, so again, the sensibility of our answer. We knew it's going to be negative because these two objects are pushing off of each other, so they're moving in opposite directions. And we knew that because this one has a large mass, its velocity will be less. This is like the dad, and this is the child over here. Okay, the child has a smaller mass, moves faster. The dad has a larger mass, moves a little bit slower than the child that has more mass. Again, the negative sign is simply indicating that it's moving in an opposite direction from the other one. And if you think about these two pushing off, that's what's going to happen. Okay? Positive, negative, that makes sense of the answer. Questions on this one? Is this becoming pretty easy, right? I'm hoping it's getting easier, and I hope it's not as bad because you also already did conservation of energy, and this is pretty similar in nature to it. but now we have two bodies interacting instead of just one. Okay, with conservation of energy, it was one object, always. Now we have objects interacting. So, spend maybe, let's see, we have a couple of, no, something like that. Oh, no, let's see, I keep forgetting the schedule, let's see, it's, I don't even know what it is. Spend like 2 minutes trying to write down your givens and picturing the scenario. That's the hardest part for this problem. Picturing the scenario, writing down your givens. If you can get them both, try to write out your equation that you would think about using here. Okay, and how it would change from the previous equations we've already used. We have 14 minutes. Thank you, Em. Awesome. That's great, because I do want to start 7-4 today. That was the plan. These C days, ooh. Don't. But there are some, if you want to grab one from my desk next door, you can. I drew it left. I should have drawn it right, I guess, because it's a positive velocity. Dang. It's my attempt at a pickup truck, I know. I'm trying. There we go. That works, right? So the pickup truck is traveling, right? It's got a beam in the back of it, like this. I could draw my beam. There it is. And unfortunately, let's say the tailgate falls out or something happens, and the beam starts to slide back. Okay, the beam starts to fall out the back of the truck. Right now, since the beam is literally on the truck, they have the same what? Velocity. But then the beam starts to slide out the back like this, which means it's going slower, and then eventually it falls out the back and the truck picks up speed. The truck's going to pick up speed because it drops the beam, much less mass. So that's logical. The speed of the beam is only 18 when it falls out the back, which is logical. It's got to be less than 25 or else it would still be on top of the truck. So the beam itself is kind of moving out the back of it. Now, in this problem, before the interaction, right? I keep using quote, like air quotes for interaction. It could be an explosion, a collision, whatever. I would model this as an explosion. Okay, this is really an explosion problem. The last one with the ice skaters, that was also an explosion problem. It was not a collision. They started together and separated. Here, again, they start together and they're going to separate. They're going to separate. So I can start this problem off by saying M1 plus M2 times VI. I know already that they're starting together. They're starting together and then they're separating. And they start together and then separate. So because they're together, we have a lumped mass. Since they separate, we have separate masses and velocities after. And I didn't even write my givens down. I'm just kind of painting a picture for you to start. This is the picture you want to see. Together, beam falls out afterward, separate. We can write down our givens at this point and list them, or we can just plug in. I know that the pickup truck is carrying 1,000 kilograms steel beam, and we're trying to find the mass of the truck itself. So let's call the truck M1, and let's call the beam M2, so that we're all consistent in what we write. So M1 is what we're trying to figure out, the mass of the truck. So in the next line, I'm going to leave M1 alone. The mass of the beam is 1,000 kilograms. The velocity of them together before the interaction, their cruising velocity is 25 meters per second. So that's everything I know about the problem before the interaction. Then the truck, still unknown mass, is moving with a velocity of 30 meters per second, while the beam falls out the back with a velocity of 18 meters per second. So why is this one, why did I save this for example 5? ones we've been doing all along. We have not seen this yet. What do you think? Yeah, we've got a missing variable in 2 spots here. Since we've done conservation of momentum, we haven't seen that scenario. It always ends up dropping off, like, oh, this one stops moving conveniently, and we could just solve for M1. Or this wasn't there in the beginning, whatever. But now we have it on both sides. So the algebraic approach is okay. You can use the algebraic approach, but to do the algebraic approach, you really need to multiply out the VI, get your M1s on both sides, factor out an M1, divide through. It becomes a little bit cumbersome. So if you like the algebraic approach and want to see that, you can definitely see that. I put it all in my notes and stuff, and I can even go over it with you individually. But for now, we're going to take the numeric approach. And to do this numerically the best way, what do you suggest I do to start? What do you suggest I do to begin this if I want to solve this problem? It's not an easy one. Not that tricky. You can definitely do it. But what's the best approach? What do you think? Steve, what do you think?
Maybe we start by multiplying out and simplifying and just sitting there.
Yeah, I'd probably multiply it out to make things more simple to work with. So even though this is a lumped mass, we don't know M1. So in reality, we're going to go back to the equation, which doesn't look like a lumped mass. So it's going to be 25 M1 plus 25,000. Again, I'm simply distributing the 25 to both of these terms. And that equals, and I'm going to start using my variables in the right way and simplifying. So again, distributing the 25 makes the problem look like this suddenly. 25,000, 18,000. Over here, this is 30 M1. Over here, this is 25 M1. And now the problem is a little bit easier. Okay, now it's a little bit easier. Move the 18,000 over and move the 25 M1 over. So take this and subtract it over here. At the same time, take the 18,000 and subtract it over here. On the left side, you have 25,000 minus 18,000, 7,000. On the right side, you have 30 M1 minus the 25 M1, which is 5 M1. So again, look at what I've drawn in red and blue to make sure you understand. We're going to move this over by subtraction, gives us 5 left. Move this over by subtraction, leaves behind 7,000. What does M1 turn out to be? 7,000 over 5. It's going to be more than 1,000, we know that much. Alex?
1,400.
Units? Remember the? Good. Kilograms, very good. All right, 1,400 kilograms. It's around 3,000 pounds. Reasonable size for a pickup truck. Okay, the steel beam itself is also pretty heavy because it's just a solid steel beam. We're assuming that it's not like a W beam or an I beam where it's a little bit lighter. Any small things that I want to point out? No, it's tough to make sense of the answer in this kind of a problem because there's not an answer with velocity, which you can argue, right? It's a mass question, so it's like, does this answer make sense reasonably? Because the number is reasonable, yes, but with my math, I don't know. But the velocity problems earlier, we were able to make sense of because they clearly have to be one negative and one positive if they push apart. So you use the context of the problem to help you. Sometimes it's a little more difficult though. So tonight, what you're working on is this 4-question part. It's really not a lot of problems, right? It's not a lot of stuff. And I think it's due tomorrow for you guys. If you look at Moodle, it's either tomorrow or the next day. But take a look, please. I think I have it due for tomorrow for you.